This is actually a project that is like died and come back and died and come back, and now it's in the back to life state. So I started it in 2011, right before I joined Google, and then I didn't do much with it for a while. And back when I started it, I was looking at this kind of weird idea I had, which is that because Go was such a fast compiler, and the language has this notion of where you say, I'm going to import this package. It seemed to me I could build an environment where when you type the name of a command, if the command had not yet been compiled, you could just compile it, and then it would run, and then the next time you ran it, it was in a RAM-FS, and it would just run instantly. And that was kind of an experiment, and I wrote it when I didn't really know Go very well. And it, like I say, it sat for a while. And then I don't know how many people know about ONIE, which is a startup that Facebook bought, which had this amazing idea that no one had ever tried before, which was putting Linux in Flash, along with a BusyBox. I went to build the environment, and it kind of almost built the kernel, and then it got the U-boot, or their command line interpreter version of BusyBox, and it just kept failing because it needed this and that package, and it needed all these other things. And at some point, I just couldn't take it anymore, and thought I'm getting too old to fool with configure scripts, so I'll see about bringing uroot back. And so some of you saw this last year at the earlier coreboot workshop in Prague, where a couple guys helped me get set up, and we actually embedded Linux and uroot in Flash on a board, and then booted it, and it came up, and when it comes up, it compiles the shell that you're going to run, and then it drops you into the shell, and then as you type commands, it compiles them. And that all worked, but I didn't really explain what it was about last year, so I thought I could talk about it this year, because we actually are doing some work with this, continuing at Google. So I'm going to talk about what it is and how it works, and then talk about the true BusyBox mode we've developed, because ARMs are not real fast, and we do have some machines with very limited flash. So it's a root file system in source form. You type a command, and the command is compiled. And if that command has packages it needs, those packages are compiled, and that all gets put in /bin, and that /bin is usually in RAM-FS for performance, although it's also in RAM-FS for size, because if you compile enough of these commands, that's a lot bigger than your flash is going to be. And then that command is run. First time you type the command, when it's compiled, it compiles it, runs it, and then they're done. And typical compilation time for most of these commands is about half a second. And that includes things like our own version of the IP command. And then there are some variations on this theme that I'll get to. But the other thing about the early days of uroot, thing I realized is, because of the way Go works, they've done a pretty good job with heterogeneity. You could build a root file system, and then you could put the 4 files for each architecture in the root file system, because the files that name the compiler are in an architecture-dependent path, and the binaries go in an architecture-dependent path. So you could actually have this little USB stick or something with maybe 4 or 8 or 16 binaries, and you'd plug it into any machine and boot it, and it would compile the commands for that machine as you type them. So that was the U in uroot. It means universal. None of this naming has anything to do with U-boot, right? Or not. But there has to be some binary, right? There has to be an init. There's always an init. So I lied a little bit. It's not all source. There's a binary for init. And of course, there's a Go compiler, and that's 4 more binaries. But the rest of it's source. All the commands are source. All the packages are source. Everything is source. And the first thing init does is it compiles a tool called an installer, which I'll explain in a minute. And then init then forks and execs sh. And because you're executing sh and it's not yet been compiled, it gets compiled by the installer you just built and run. So you have one program compiled ahead of time before you boot, and then init has to compile the installer when you boot. And then from that point on, everything you run or exec will be compiled when you exec it. So the init in this thing is 206 lines. So it's not, these commands tend not to be big in Go. And this is the thing I mentioned about how it could serve multiple architectures, but this is the coreboot workshop, and we'd really only put one version in firmware for one architecture, so I'll kind of blast through that slide. And so here's where the coreboot part comes in. Not everybody wants to source in Flash. We've seen that, and not everybody wants to wait for compilation. And I even had someone tell me they wanted to be able to run commands and not have fork or exec run. So there's a fairly crazy mode that we've been able to build this thing in where it doesn't even use the fork and exec system call to run your commands. It uses the Go's built-in parallelism or concurrency operations. Some Flash parts are just small. They're only 8 meg, and really realistically for the source-based version of uroot, you've got to have 16 meg. So again, where like a year ago in Prague, I really only had the all-source version. Since then, as different needs have come up, we've taken different forms with this thing. But the source code never changes, so you don't find yourself writing a special version of DD, say, because you know you're going to be embedded. The way it works is you write DD, and you have a standalone DD, or you have the DD that's kind of built into the giant binary, which is only actually 400K, but you know, you don't do the kind of thing you do in BusyBox where you write special smaller versions of programs because you know you're going to be embedded. So here's some variations. The top one is just, I don't have a better name, so I call it max. There are 5 binaries per architecture. All the commands are in source form. It's all dynamic compilation, and there are multiple architectures supported in one root device. So this is kind of the post-boot model. You've got a local disk or a USB stick or something. You're going to boot, and then you're going to have this root file system that you mount, and then things get dynamically compiled. You might pre-compile some binaries because you want things to be a little faster, so you might have some or all the commands pre-compiled. Still doing dynamic compilation. And I think the mode that's kind of more interesting for the coreboot case is you've got 5 binaries, but all the commands are in source form. You do dynamic compilation, but it's only one architecture. And again, this is what we did last fall when we installed this on a motherboard with 16 meg SPI part. And then if you've only got, you know, a much smaller thing, like an 8 or 4 meg part, then you have this way of compiling all the commands into one binary. And I'll touch on that toward the end of the talk. So, but the max, just to give you an idea of the rough look, this would really, if we only had one architecture supported, it would just be fewer binaries. There's a standard kernel, and then actually Go is changing a little, so it's sort of, I don't know, 5 or 4 or 2 Go binaries per architecture. I'm not so sure anymore how many, but there are fewer. And you know, those binaries have names like 5G and 5C and 5A and 5L. They kind of picked the Plan 9 naming convention for compilers. And then they go package source. And all that stuff packs into 13 meg with LZMA. So that's kind of the rough sort of layout. And then the root file system actually looks like this. So at the upper left there, you see the various architecture and OS dependent directory naming. So there's Linux underline AMD64 and then the init binary. And then the next step down is all source. So there's source commands, cat, and then under the cat directory would be cat.go. There might be other packages we have to bring in, like github.com based packages that would also be in the source directory. And then we have the Go source tree. So we have /go down there at the bottom left, and then /source. And then there are really no packages pre-compiled, but you need a Go package directory, and then that Go package compiled on demand, that kind of gets filled in once you boot. And then finally, you've got to have some sort of toolchain. So there's a Go Linux AMD64 Go binary, which is sort of the builder. You can almost think of it as the make for Go. And then in Go package tool Linux AMD64, in that directory there would be binaries for the Linux AMD64 Go compiler and so on. And again, in the coreboot case, we only have one of those sorts of binaries. We've either got the Linux AMD64, Linux ARM, or whatever, and you know, we limit it that way. So at boot time, init builds a couple of directories and does the basic mounts you need done, like proc and sys and all that good stuff. You can see a directory here named build bin. That's created by init. That's populated with symlinks. And then there's a directory called bin, which begins life empty. And one last binary is put in build bin called the install command. And then init creates etcdev proc and does whatever's got to be done in terms of mcnod, that sort of thing. Because you've got to have dev null there or nothing's really going to work. So there's basic things you've got to have. So what happened? I'm sorry, I forgot I had to take a slide out for space. So what happens when I type cat? Build bin is in my path after bin. So if I type cat, it searches bin, doesn't find it. It then searches build bin and finds cat. It's a symlink. Install command gets run, and cat is the first argument. So install command says, fine, I'll build cat, put it in bin, and I'll exec bin cat. And that's how that first iteration where you have to dynamically compile it and run it occurs. And then from that point forward, since bin is in the path before build bin, you'll get bin cat. So it's really, because these are statically linked, it's actually pretty incredibly fast. When you get enough commands built and installed, they just tend to sort of run. And surprisingly, you can really feel the difference between running a dynamically linked cat and a statically linked cat out of RAM. It's more than just putting it in RAM. It's avoiding all the stuff that comes nowadays with shared object libraries. So that's fine, but what about things like scripting? And we've got kind of a rather unusual way of doing scripting and build-ins. For scripting, we take fragments of Go and we wrap them in a main and turn them into a program. We automatically figure out what imports that needs, then we compile it and run it. So when you throw a script at this environment, we compile it and run it, and it's fast enough that it really isn't a problem. But if you want to have that persist, you can create a build-in, and we actually recompile the shell and then run that shell. So you actually get a custom shell with your custom build-ins. And if you've ever watched System 5 init scripts and the fact that they sort of source the same script literally thousands of times as they come up, you could imagine setting up a shell with build-ins, and you'd compile that shell once, then you'd have sort of a shell that's customized to the function of booting your system. So one of the things I like about this is the shell and build-in language is Go. It's not something my shell can interpret. So I'll never need to set up a website where people can paste their bash scripts and validate them as not having bugs, which actually happens nowadays. It's one language for everything. The language is Go, and it's compiled, always compiled. So we use Go to write Go. We use Go to write Go for scripting and making new shells and making these little precompiled things in memory. So here's an example. The shell in uroot understands the command script and it knows what to do. And in this case, I'm going to create a script for the IP link command. So you can see the keyword script and then a left curly. And the script command knows that if it sees a left curly, that it's got to sort of wrap this thing in a little bit of boilerplate and then generate the imports. And in the case of this example, I've taken out all the error checking for space. First thing I do, I iterate all the interfaces and assign that to a variable called ifaces. And then ifaces is actually an array of these interfaces, so I do a for across the range of ifaces. And adders gets me all the addresses on all the interfaces in that one instance of an interface. And I'm sorry I'm rushing. If there are questions about this syntax, let me know. And then finally I print. So a couple of things here. The colon equal form in Go means declare variables on the left and give them the proper type. So net.interfaces returns an array of these interface structs, and this actually creates that variable. The for here, v is assigned with the value of each of the interfaces in the range. This here underline there could be an index, but we're not going to use it. So for all the things in this range, v will get that individual interface. And then adders is another new variable, and it gets assigned the value of the adders. Finally, in this format, the %v in Go means I really don't know how to print this, but I know you do because you're a smart language. So just print this in some form that will make sense to people. And so I say %v has %v, and I give it the interface, which was the thing in the for loop, and then the adders through that interface. And when I print it, I get something that's not too bad. The present v for v says, oh, this is an IP interface. It's index 1 in the array. MTU's 1500. Its name is Lou Beck. It's up. And here are the IPs it has. And notice it has a v4 and a v6 IP. And then, again, for the ETH0, I actually get to see the MAC. It's up, broadcast is enabled, and there's my v4 and v6. So that's kind of, IP link. And if you've ever looked at the IP command, it's just a bit longer in C. So the go script command rewrites that fragment and uses the go import package to figure out, what it needs to do. And the way the import package works, it's not sort of textually based. It actually parses the program and produces a Go abstract syntax tree, and then finds things that are imports and then fixes them up. And it's actually a little more complicated, and I'll get to that in a second. But here is what happens with the boilerplate. The script command put package main here, and it put func main, and then there's the stuff I had in the script. And then the import thing actually inserted it, figured out and inserted the import net and input format. And this actually is a little complicated, because if you look, this is really not, it's not textual. It actually has to look in the net package and make sure there is a thing called interfaces, or this will actually not work. So import won't generate something unless it's valid. And it really even had to figure out, well, this variable v was from iFaces, and work it back to, oh, it came from here, and address is actually valid for that variable. So it's actually a very tricky thing, and it's, I was kind of impressed when I saw how well it worked. So, but what if you want a built-in? Normally when you do a built-in in Bash, you write it in the Bash language, and the Bash has to interpret it. And every time you kind of kick off a new Bash, it actually interprets that built-in command all over again as it pulls it in. And what we do instead is we build a new shell. So we give you a brand new shell, and that new shell has been extended so that it has those new commands. So here's what a build-in looks like, and in fact I'm doing two build-ins here. The first build-in is hi, and it'll print hi, and the second build-in is there, and it'll print there. So this looks a little different from the script command in that I have a name of a thing, and then here in the quotes I've got sort of the fragment of Go code that has to run. And it's a similar process with a slight difference. Firstly, I've got to take the existing shell code, which is in source command shell, and put it in a temporary directory in temp. And then I generate the two fragments for the two build-ins and drop them in there. Then I build the shell. And then I drop you into a private namespace with this shell replacing the shell that you would normally have. So the result of one of those commands would be we'd get this, again, boilerplate. So in this case, the CD built-in, you say package main because it's part of the main shell package. Here are my import statements. This init statement is like a constructor, and it calls the function add built-in, and the built-in has the name CD, and the function for the built-in is CD. And note in Go, there's none of this forward declaration or prototype nonsense. It just works it out. And then every built-in in the shell takes a string, which is the name of the command, and then an array of arguments, and then returns an error, if any. It can return nil, meaning there is no error. And in this case, in the one error, if you do a CD with more than one argument or no arguments, that's a bug in CD, isn't it? Because 0 arguments should mean, print your current working directory, or I guess, or something, or CD to tilde. But if the length of S isn't 1, then I return, an error, and otherwise I do the thing and return the error from OS.shadur. So these are basically the steps. You create a unique temporary directory, as I mentioned, and copy the source, and you use some of the goodness of the Linux private namespace stuff to do it. And that shell is there as long as the thing that invoked it is there. Any children of that shell will run that shell if they run a shell. And then when all those things go away, the shell just kind of evaporates. So kids get the build-in, and when the shell goes, the build-ins go. So anyway, the importance of that, I guess, is that we take code fragments and we rewrite them, and we produce new programs in new shells. But I had a request for a single binary version of uroot for the QB board And that's the Allwinner A10. Wonderful boards, but they're not super fast. And when you kind of watch the dynamic compilation go on, it got a little old. It could take 30 to 45 seconds just to get to a shell. So question was, could we compile all the uroot programs into one program? And you may remember I mentioned that Go AST package. So I can take the commands and rather than sort of rewrite them as in BusyBox to be built into a shell, I can write it. I have a command called BB, which stands for BusyBox, which will take all kinds of Go programs, and using that AST package, we rewrite them. Then we drop them into a directory along with the shell source, and we actually build a new shell, much as we built a new shell for build-in that has all the commands wired in. So this is the case of the ls command. The ls normally is package main, and it has some flags, and it has a function, and this code I have basically transform it so now it's the package ls, which gets built into it, and all the strings are renamed to ls.l, but I nicely sort of don't require you to type ls.l. You can say ls-l, and I translate the switches. And then just for fun, I renamed the function to be capital M main. Well, that's kind of required because of the way Go exports work. So, and in an extreme case, which we tried, we can even have the shell not call exec. You can just call the build-in rather than forking and execing and then calling the build-in. It can actually never fork and exec. So the Go size penalty is gone. With one Go program, it's about 2 meg. 33 programs fit into 7 meg, which compresses to 400K. And the things I have in there are things like DHCP, wget, ping, the IP command. I've almost got kexec working. So we're pretty close to being able to do the kind of neat thing that John Lewis has been doing with Jeltko, where we do a wget and then we do a kexec and start a new kernel. We don't have a wireless stack yet. That's kind of the next big thing, but that'll come along. And actually converting these 33 commands and turning them into one binary in a shell that is all built up and everything. To do the processing and rewriting takes 0.2 seconds. And again, it's not rewriting in place. These commands are copied somewhere else to be rewritten. And the full build of it all takes 12 seconds. So the configure script alone for BusyBox takes considerably longer. This is actually the complete and full build of the entire system. So what is this good for? We've kind of got an interest where I am in building safer startup environments, and I think the easiest way to translate that is things that aren't written in C. So there are some security people who are very, very interested in this mostly source-based root file system because there's a certain level of verification they can do when they come up, and we can also make it very compact because most of it is source. We can actually jam this thing in a firmware, say in a Chromebook, and then because it's so small, we can really have a very long key when we verify it. And if we really believe we trust the binaries that comprise the Go compiler, some way we produce them and a way we trust them, that's just a whole lot less binaries to worry about trusting. There's the source and there's the 4 compiler binaries, and we're done. That's what we have to verify. So I like it for that. I also like it for the fact that I've been learning a lot about how things work. I really didn't know how the IP command worked, and now I kind of know how the IP command works, and I'm learning a little more about it each day. And I think I'm going to try and learn how all these wireless things work. I'm uncomfortable with the idea that I'm being reduced to install this binary package, install that binary package to get things to work, but a lot of this stuff doesn't even compile except under the most happy circumstances. So in the case of Go, it's going to compile, and I'll be able to actually read the code and see how it works. So if you want to try it, you can get a pre-built Docker. Unfortunately, that's kind of an older version of the system. I do need to update it. But it does give you a good feel for the dynamically compiled version. And the source is at github.com or Minnich uroot, and we've been working to make it sort of a lot less work. I had a summer student, and we really improved the friendliness of the construction process. So things are just a lot easier than they used to be to put together. Generally, it's kind of run one command, and you get an init ramfs that you can build into a Linux or put in a syslinux command. And I think I ran over, so I am going to stop. Let me stop screen sharing. And if there's any questions, just let me know, or if you want to talk to me later, let me know. We're always looking for people who want to learn Go or who know Go and want to contribute. So I'm really happy if anybody wants to get involved. Oh, and there's my coreboot shirt. Thank you, Vladimir, for the new one.
So Ron, there's a question on IRC.
Oh, okay, good. Because otherwise we'll get. I know. I no longer remember why I need that. There was a reason, and it's been so long, I just don't even remember what it was. Do you remember, Paul? I mean, you asked the question. Maybe you know and I don't.
It's because your namespace.
Ah, okay. That's what it was. Yeah. Thank you, Patrick, for explaining my command line to me. Any other questions? All right. Well, thank you. And again, if you want to contact me offline, we're actually looking at this for Power, ARM, and x86. So we have interest in that kind of range of platforms. And thanks again.